Okay. Well, it's getting bigger than that, looks like. So let me try to figure out how to change slides. How do you do it on a Windows machine? Oh, now it's doing it. Okay. It's working now, the arrows, but they weren't working before. F11. All it did was take away that. Okay. Windows. All right. So last time, what did we do? So I don't remember if we started on these lectures last time, but so we've been doing some investigation of renormalization, and so we had. Let me try to remember. So we had computed a. Okay. So we had computed our scattering process at next to leading order. We found that we could renormalize it, and we could do it order by order, right? But there were still logarithms that would diverge in the massless limit. We wanted to work in the massless limit because we're at high energies, and our particles are, relatively light. And so we felt like we could simplify things by taking the massless limit. But the problem is we have these logs that typically go like, some invariant, whether it be ST or U, over the mass squared. Okay. And so we tried different things. We tried to incorporate real corrections. So the emission of extra particles off of our initial or final state particles. We computed that, and we ended up finding that it canceled some of the pole or some of the divergence, but it still left it over, and it actually introduced another log, another large log that depends on the angular resolution of the detector. Right. So what that's telling us is that as experimentalists build better and better detectors, we'll have to go to higher and higher orders in perturbation theory, and that's exactly what happened. As people moved from the early 80s when they were at CERN, the machine SPS or whatever, where they discovered the W and Z boson. Now, because detectors have gotten so much better, it's forced theorists to compute things to higher orders. Okay, so that's where we were at last time, and so we said, okay, well, maybe there's some conceptual problem, right? Maybe we screwed something up when we were doing our renormalization. So we said, well, let's just do the bare minimum, right? And let's just make sure we cancel the poles, right? So when we compute these things and we get these 1 over epsilon UV poles, we're just going to tune our counter terms just to cancel those guys off. And we'll leave the logs of, the scale mu alone, and we'll leave all the constants alone. And so we did that. And what we found eventually, so here we're computing corrections to the mass, the physical mass, right? So we made a distinction between the physical mass and what we call the bare mass. And in the end, we found that when we did this, we computed things in this minimal subtraction scheme, that sure enough, the poles go away, or the divergences from the massless limit go away. Right? The bad thing is that we're left over with some dependence on this unphysical scale, this renormalization scale. And like I said, there's nothing we can do about that, the log that depends on the angular resolution. But the important thing was that now we can safely work in the massless limit. We just have to make sure we use this MS bar scheme. We just cancel the poles. Okay. And so that set us up to investigate kind of renormalization schemes and the renormalization group equations in general. So, trying to compute how, one of the things we discovered was that if we want observables to be independent of, independent of scales or independent of, the normalization energy, thing that we introduced, it means that our couplings and our masses and any other parameters are going to have to depend on the scale mu, right? And they have to depend on it in such a way that they cancel each other out, so your observable is independent of the scale mu, right? So we worked through taking that observable cross section, if you will, t squared, and went through a little trick and found how the coupling alpha depended on the scale mu, right? So we took a derivative with respect to natural log of mu, right? This thing we just saw on the previous slide depends on mu, right? But we argued that alpha and the mass parameter have to also, depend on mu, so they all cancel out. All right, so this left-hand side would be independent of mu, and so you take a derivative, you get 0, and on the right-hand side, so alpha is obviously dependent now on mu, and you can work out a differential equation that describes how alpha does depend on mu. And this is a special thing. It's called the beta function. It's very important when you talk about theories. And we saw some example of that because you can solve that differential equation really easily, right? And what you find for this phi cubed theory is that, so what you do is you define alpha at some reference scale, right? So, whatever your mass scale, a good mass scale might be, and then you vary that renormalization scale around that scale, right? And you see what happens. How does the coupling behave? And so in this case, we found that as we varied the scale, the coupling, or as we increase the scale, the coupling decreases, right? So as we go up in energy, the coupling gets smaller. Right? This is called asymptotic freedom. It's the same thing that happens in QCD, right? And just like in QCD, as we decrease the scale, as we go lower in energy, the coupling becomes non-perturbative. Right? Coupling grows and grows and grows, it gets larger than 1, and then you're outside the realm of perturbation theory. And this is what was I going to say? I don't know. I lost my train of thought. But this is exactly what happens in QCD, and explains why things bind into pions and protons and neutrons and all that stuff. Okay, because the coupling's so huge, so large that you can never separate out those quarks and gluons that are inside of it. Okay, we'll see when we do QED that the beta function there is positive, right? And what that translates into is the opposite behavior, right? So as we increase the energy, the coupling gets larger, and as we decrease the energy, the coupling gets smaller. The thing to remember about that though is that the dependence isn't as strong, so it's it's not as sloped or severe as QCD is. All right. Okay, so as we summarize what we did, and then I showed you guys kind of a general way that you can compute these things. So we don't want to have to, when we consider a theory, we don't want to have to, calculate some really hard cross section next to leading order in order to extract this dependence on mu for the couplings or the masses or whatever. Right, so what we did was we developed a kind of a recipe for doing that. So you're given a theory, right, and you want to see how does this thing behave. How does the coupling behave with this theory as I vary the scales, right?
So that it doesn't depend on any region of the energy that we calculate this coupling.
What doesn't?
For example, you say that this formula is true for the 1 TeV energy. If we increase it to like 100 TeV, we have a different formula. What is the same?
Well, it depends on. It's technical. I mean, it depends on what particles. So in this theory, we only have one particle. We only have one particle, right? So independent of what scale we're at, the behavior is the same, right? But there are theories like supersymmetry where you have particles down here where we live, right? But as you increase the energy, you get above the mass threshold for those guys, so you can produce those guys virtually, right? So they'll contribute to the self energy and stuff like that. So then you might have some shift in the behavior, right? You might have some nice slope, and then all of a sudden it hits the SUSY scale and it has some discontinuity to it. Yeah. But then in this case, the behavior is just what it is, right? There's no big shifts. So the starting point of this recipe for calculating the mu dependence is to write down the Lagrangian in two ways. One, the bare Lagrangian, where the fields, masses, the couplings cannot and do not depend on the scale, right? And the other way is what we've been working with, which is the normalized Lagrangian. And there you have your counter terms. You've got this mu scale that we've rescaled our coupling here so that it's dimensionless in whatever dimensions we're working in. Here we're working in 6 minus 2 epsilon, right? But the important point is we're using the MS bar scheme, and probably all the way through next semester we'll use the MS bar scheme. Okay? It's the most handy and easiest to work with. So what you do is you write down the Lagrangian in two ways, and then you compare the two, right? And you make kind of one-to-one correspondences between the parameters of the fields in those two Lagrangians, right? So you start with the field, and you see that how those two are related through some factor of the counter term, the masses, the couplings, and the other counter terms and stuff like that. Okay. And so what you do next is you say, okay, you reason that we've seen that these counter terms, they start at order 1, right, but they contain poles, right? And I told you guys that when you're at one loop, like we were, you always have just single poles, right? But you'll run into cases if you're computing 2 loops, 2 loop corrections or something like that. God help you if you have to do that. But if you did that, you would run into double poles. Okay, so there you have double the pleasure. Okay, so we can generally expand these guys as a linear sum over poles, and these poles have coefficients. And so we said the same thing for the coupling guy. And we said, well, we've already computed this for phi cube theory, right? We go back and we compare to what our counter terms that we calculated a couple weeks ago, and we see that we can write down what the first coefficients are for the single pole. Okay. Right, and then we use the same kind of trick that we did with the cross section, right? So we take these relationships. And what we'll do is we take natural log. The first step is we take natural logs of both sides. Right, that separates out the counter term dependence from all the other couplings and parameters that show up in these guys. Then we take a derivative with respect to the natural log of mu, right? And then we argue that the left-hand side, which is typically the bare Lagrangian parameters, we argue those guys cannot depend on the scale mu. So that derivative gives us 0, and then it's just a matter of solving the equation on the right-hand side. Right? There's a couple leaps of faith, right? You have to argue that at some point, when you write down this expansion, it looks like you have some divergent coefficient here, right? But you say, well, I'm talking about a physical theory, and we know physical theories, observables, don't have divergences, right? So we somehow, in that expansion, these coefficients, G1, G2, and on down the line, they conspire to cancel out each other, right? So what's left over is something finite, right? So at most, you can start at order 1, which would be, some function of alpha that's called beta, and then you're allowed to add in terms order epsilon or higher, because in the end you're going to take epsilon to 0, right? So you can conveniently choose it to match what you have from your kind of explicit calculation, and you go through that. You do plug in what you have for the coefficients, and bam, you get the beta function. Okay, and you find that when you compare with what we got earlier from the cross section type of calculation, that it agrees exactly. All right. So you can do the same. I don't know. Did I stop there?
I think Yeah.
Okay, so you can do the same thing for the mass parameter. So I think that was the first thing we did when we were doing the cross section was extract the mu dependence of the mass parameter. But you can follow the same recipe, right? So you write down your relationship between the bare parameter and the normalized one. You define some function because you know you're going to take a natural log. So some function of these counter terms. But you follow the same recipe, right? You assume that these counter terms are, linear expansions in the poles, right? You can expand. You're assuming that these coefficients A and B, are higher order in alpha, right? Higher order in the coupling, which is small, and so you can expand this. So you're forgetting about, for the time being, that you're going to set epsilon to 0, but you can do an expansion. You can write down the function, and it just looks like that. All right, so you can say, okay, well, I can pull out the dependence on the sum over epsilon n and define some new function it just depends on alpha. Okay, and that's what we're after. We want some coefficient of these poles. Okay. And in particular for the n equals 1, which is the single pole, you find that this function is just minus 5/2 alpha, whatever it is. Right? It's just some number. Okay? All right, so from that point, we say, okay, all right, let's take our relationship between the bare and the normalized masses, take the natural log, right? So that gives us the m function plus the natural log of m. And then we take a derivative with respect to the natural log of mu. We argue that the bare parameter or bare mass parameter can't depend on mu, so it has to be 0. Right? And then we're left with the right-hand side. Okay? And luckily for us, we've already computed what this guy is, the beta function, so we can just plug it in, right? And we do some other manipulations, and we can rewrite this thing in terms of just the derivative of the mass, right? So it turns out to look like a differential equation, and if you solve it, you get something that looks like that. So this is, so this anomalous dimension is actually that stuff, right? The natural log derivative, okay? And you find that you get this thing called the anomalous dimension, and it's minus 5/12 times alpha, okay? It'll depend on what theory you're in, what that coefficient is. But the important point is that using this simple kind of algorithm, we were able to reproduce what we got from our next leading order cross-section calculation. Okay, so finally, you can do this. Most of the time, you'll just stop there. Right? You're just interested in how the physical parameters evolve with mu. But you can also look at things like the propagator, right? So we can write down a relationship between, the propagator and the renormalized theory, which looks like this. So it's the correlation function, but we're taking a Fourier transform, so that's where this stuff comes from. Okay, but you make a comparison between that guy and the bare one, the bare propagator, right? And you follow the same recipe. Okay, so you see that the renormalized guy depends on two factors of the field, so you're going to get a factor of z phi, right? Because those guys scale like z phi is 1/2. Where am I? All right. Yeah. So you do the same things. You take natural log, you take a natural log derivative, you argue that the bare propagator, which in theory, includes all orders of perturbation theory, so it can't depend on mu. You argue that the thing is independent of mu, you set it to 0, and you take the derivative of this thing, the propagator, with respect to mu. But this thing in general can contain factors of not only mu, but also alpha, the mass parameter, and any other parameters that you have in the theory, right? So if you had 15 couplings in general, you'd have 15 derivatives there, right, for the couplings. Okay, and that'll be homework next homework. Right, so you can do the same stuff. We've already computed this Z phi thing, right? So you can expand it, and this is what it looks like in expanding and epsilon. And so if you take the derivatives, all that stuff, you get minus alpha times A1 prime. And we already know what A1 prime is, so we're good to go there. And then finally, you can just define, because we know all this other stuff, right? You can do change the variables and things. So we know what this is. The beta parameter is the anomalous dimension. So you can just plug stuff in and get how the propagator depends on the normalization scale, and that's called the anomalous dimension of the field. Right? There's an anomalous dimension of the mass and an anomalous dimension of the field, and I have no idea why it's called anomalous dimension. Probably has to, I don't know, but it's just the dependence of these guys on you. Okay. And the equation for the propagator is a very important equation. I've never used it in my life, but it's an important equation. It's called the Kalin-Szymanczyk equation for the propagator. Okay. And in general, it's not just for, so you could write down, this is what it looks like for the propagator, but you could also do it for any endpoint function, 3-point vertex, 4-point vertex, and so on and so on. Okay. And you see that it's dependent on the beta function and the anomalous dimension of the fields and masses. Okay, that's just kind of a general feature. Okay, let me get out of this. How do I get out? What? F11? Okay. All right. So this is Ava's time to shine, because we're going to talk about condensed matter physics, okay, and the connection between condensed matter and QFT. Okay. All right. Okay, and I noticed I got carried away. I must have gotten carried away with changing colors and stuff, but you can see by the fourth or fifth slide, I get worn out. It's black and white. Okay. So what we've been doing is, the last couple of lectures, we've kind of derived or come up with a general theory of normalization. It's a systematic way that we can, flush out all the mu dependence and find how our theory behaves, right? With the changing of this renormalization scale, right? And what we've seen is that these divergences that get renormalized, they always come from the high energy part of the spectrum, right? They always came from those loop integrals where we let k go to infinity, right? And that's where those poles were coming from. Right? But if you think about, when we talk about dimensional analysis, high energy corresponds to small scales, right? And so what we're going to do today is kind of explore this, I don't know what you call it, this relationship, or this kind of, I don't know, the relationship between the high energy behavior of QFT with the low energy behavior of condensed matter physics, okay, or statistical mechanics. Right, so we kind of just accepted, when we ran into these poles, I told you guys that you either accept it and move on, you can go on and live your life as a theorist, or you say this is crap and walk out of the room and you become an experimentalist, okay? But in this class, the people that remain here have come into what I call peaceful coexistence with the divergences. In other words, we've seen that these divergences pop up all over the place, but we have a good way and a good argument of how to cancel these guys. Okay? And when that happens, when we're able to do that, we say the theory is renormalizable. Okay? So what I want to do today is try to get a deeper understanding physically of where these divergences come from, and we'll so it's not going to, it won't be today. It'll be later in these lectures. We're going to do that. Try to get a deeper understanding of where these divergences come from. And the way we're going to do that is kind of an indirect way. We're going to steer off and talk about condensed matter physics, okay? The behavior at small scales and second order phase transitions and all this stuff that condensed matter people always talk about that I never understand. Okay. So what we'll do later is we'll talk about this direct approach to understanding the UV behavior of theories. And this direct approach is due to this guy, Kenneth Wilson, who in high energy physics in the theory world is like a god. He's the father of lattice QCD. So he's I don't know. He was the father of a lot of good physics, a lot of low energy, non-perturbative physics. Okay, and we'll cover his approach to that, and we'll discuss his importance in the field. But first, let's take this sidetrack and talk about some condensed matter physics and try to make a connection. And we're going to see that there's a connection between these UV divergences in QFT and fluctuations near second order phase transitions. You guys know what second order phase transitions are?
I'm sure I've heard of it before.
Do you know what a first order phase transition is? I don't either. I always have to look it up. Yeah. That's the same one. I think.
Liquid, and solid, gas, stuff like those transitions.
Yeah. So that's what I'm talking about. Okay. So it's you're close. I think close enough. Okay. I'll talk about it. Okay. So this is my, nobody ever gets this reference, so I'm just going to skip it. It's from a movie called Usual Suspects. You know it?
Yeah.
Oh, you guys know it? Oh, okay. Yeah, so you can think
That's
of.
the one I've heard of it, but I've never seen it.
Okay, well, I won't spoil it for you then. All right. So let's not spoil it for Jordan, and he can go off and watch the movie this week or this weekend. Okay. Don't be fooled by appearances. A lot of times, in the physics departments, high energy people who use QFT and condensed matter people who use density functional theory and all these other things that they use, they always butt heads. And I've never understood why, because the stuff they do is so interrelated. They're using the same mathematics that, they should be talking to each other. But for some reason, they always hate each other. I don't hate condensed matter. I think they're kind of cool. But I don't understand what they do. Huh?
Unless they're experimentalists.
Yeah, no, I'm not, obviously I'm not an experimentalist. Okay. Okay. All right, so what we're going to do is try to make this connection, okay? And I've already told you that, our poles are coming from the high energy scale, which tells us that, it's from this very small distance scale. And actually, this kind of cutoff, we've always introduced cutoffs to regularize these poles. That idea is not, just exclusively owned by QFT, but it also pops up in classical field theories, right? And so there, at the beginning of the semester, when we were developing quantum field theory, we went through this phase where we talked about classical field theory and we talked about the rod, right? And so there you would have, we developed kind of a continuum treatment of that rod, right? But if you were to probe that rod smaller and smaller, you get to the point where you would start seeing atomic type effects, quantum effects, right? So that would be a natural cutoff for our continuum theory, which would be, so we would say, okay, we can, apply this theory down to some atomic scale and we're all good, right? But what happens is you can, near that kind of transition between, macroscopic and microscopic points of view, the macroscopic physics, if you're on this side of that cutoff, actually start to show some dependence on what's happening microscopically. Okay. All right, and that's what we're going to see in just a second, and that's what we call these. We'll relate it to second order phase transitions. Okay. So what we're saying is that by understanding the small scale, the microscopic scale, we can compute the parameters at the larger scales. Right? So if we understand quantum mechanics, we can describe how this big block magnet is going to behave. Right? When we put it in a magnetic field or whatever you guys do. Okay? Change the temperature. What else do you do? Electric field. Okay. And so now, you say, okay, that's all good for condensed matter physics, but what about QFT? Well, the correspondence of that in QFT is that we have to have precise knowledge of the high energy scale, right? And we just don't know, right? We just don't know what the high energy scale is. We tried to develop theories, develop grand unified theories, and nothing that we've written down so far works, right? Because at some point something breaks, right? And you have to introduce all this unnatural stuff, and that's what happens with Susie. Susie at high scales, and, when you see it on paper, is beautiful, but then as you get lower and lower scales, you have to introduce all this crap to kind of take, like I talked about R parity, right? So they found that as they went down in scale, they started having protons decay, and we've never seen a proton decay, right? So you had to put in some mechanism that protects against that. Okay. Right. So, so what am I saying here? Right. So, in QFT, the best we can do is for physical parameters like masses and couplings, we just have to rely on experimentalists. We've seen that in our renormalization conditions, right? We always have to take the measured value and use that as our kind of normalization condition, right? Right. Yeah, I don't know what I'm trying to say there. I said the most important stuff, so we're good to go. Okay. All right. Oh, I know what so it's related to Hussein's question, right? So if you want to compute, an effective theory at lower scales, right? Or compute like the mu dependence of couplings or masses and things like that. What you do is you basically start, at the high scale and you integrate your way down, right? So integrating down or integrating out means you start at some high scale where you have this really nice theory like Susie, right? But we don't see Susie particles in nature. We haven't seen them yet, right? So as you go down, all right. So let me say, so at the high energy scale, you would have this whole kind of zoo of new particles, right? But as you go down in scale, you cross their kind of mass thresholds, right? And so you do what you call integrating them out. Okay, so you have a well-defined way of getting rid of the particles, but still, even though you're below their mass scale, they can influence the physics at a low scale, right? And that's in fact how we, before the top quark was discovered and before the Higgs was discovered, things like corrections to the W mass or the Z mass, we computed these things to very high precision, and you can extract the dependence of the mass of the Higgs or the mass of the top or whatever, right? It's an unknown particle. Just from that precise measurement, you can extract because if the Higgs is like the Higgs is what it is in the standard model, you can calculate its contributions, right, to that whatever that observable is. It'll be like a log of the mass of the Higgs, right? And so then you compare that number and you just solve for the mass of the Higgs, right? And that gave us a pretty good idea. I mean, we were, the mass range for the Higgs was pretty wide open. It was like from 90 GeV up to, multi-TeV range, right?
Wow, it took so long to find it.
Yeah, but we had whittled down because those large masses would have had large kind contributions to the observables like the W mass, right? And so we were able to whittle it down to a small window between 100 GeV and 200 GeV, right? And when you consider the free parameter space that you had to work with, that was pretty remarkable, right? Okay. Right. So in QFT, the low energy physics, right, depends on the degrees of freedom of particles that are closer to what we call the fundamental scale, right, fundamental cutoff scale. Okay, so we've always assumed that the cutoff scale is large. If it wasn't, we would run into problems. So we've always worked under the assumption that the cutoff scale is large compared to the mass. So we were able, in a sense, we're tuning the mass to be small. Okay, so this might seem, if you're not used to this, it might seem arbitrary, natural and kind of ad hoc, but it works. Okay, it works. That's all I can, say. Okay. And so this, I think this is a typo. Yeah. So what we do, the fact that we're able to compute things at small scales from large scales, even though we're doing some of this unnatural stuff, gives us some hope that maybe we can do the same thing in statistical mechanics, right? In other words, be able to compute things within that region where you're making that transition between macroscopic and microscopic physics, okay? Where the cutoff is. Okay, so let's consider just a very vanilla standard condensed matter system, okay, because that's about as far as I can go. All right, so it's going to be a magnet or some material, right? And the electrons have their spins, right? And we know that when we're at high temperatures, right, generally, or even at room temperature, the spins of these guys are randomized, right? They're all pointing different ways, okay? I'm talking about a ferromagnet, okay? I don't remember the differences between the two, but if you do, it's important, okay? All right, so at high temperatures, the electron spins in the magnet are disorganized and fluctuating, but we know that as we lower the temperature, things start to align, right? As we lower the temperature, the spins and these guys start to align, okay? But how do they align? On a large scale, right? So you've all seen that picture, right, where there's only a handful of spins. But what about, a truly, macroscopic piece of this material, right? Well, we know that, as the magnet cools, you're going to form clusters, right? So, you might form, some clusters here that are pointing up, some clusters here that are pointing down, and those clusters start to merge, right? They start to merge until finally you get these giant clusters, right? So you would have this one giant cluster, but you still, even, when you're close to that kind of critical temperature of going completely, one direction, parallel or anti-parallel, you still have these pockets of the opposite behavior.
Okay. Looks like we've got pockets within pockets.
Yeah, exactly. Okay. Yeah. Okay. Oh my God, it's a lot of words. Okay, so what you observe. So we were talking about a ferromagnet, and what you observe is that the same type of behavior happens in other second-order phase transitions. Okay, so ferromagnetic, making that transition from randomized to magnetic or spins align, is a second-order phase transition. And you actually observe the same behavior in other types of materials and things like binary alloys, which I have no idea what that is, critical points in fluids, or the superfluid transition in helium-4. The important thing is that one phenomena describes these very different things. Okay? That's from observation. Right. Right. So what we're trying to do is we're trying to make a connection between this second order phase transition and the behavior of QFT. God, these are just too many words. Right. So, okay, so basically it boils down to, in QFT, we've seen this, over the past week, and we always make these arguments that physical observables have to be independent of they can't be divergent, right? We've always argued that they have to be finite, right? Well, if you use this kind of correspondence between QFT and condensed matter physics, what it's telling you is that the fact that you're independent of that high scale basically translates into in condensed matter that the prediction of these statistical fluctuations, right? So these that picture that I had up before of second order phase transitions that in theory the behavior or this phenomena is universal, right? So it can describe not only ferromagnetics, but it can whatever binary alloys and all that other stuff. Okay, and that's what we're going to see. Okay, so we want to kind of we want to see this connection, okay, between the cutoff independence of QFT and kind of the the universality of this phenomena that I'm talking about. Okay, and what we'll see is that understanding one gives insight into the other. All right, so let me just stop for like 2 minutes and get a drink of water because my throat is like killing me. Okay, all right. When's the qualifier coming up? 20th? 27th? So 2 days before school.
Yeah. I remember that.
You guys ready? Supposed to say yes.
It's on the email. It's on our email. Yeah.
It's usually,
It's quantum and classical.
oh, it is?
I
Yeah,
can't do anything, but
Maybe that's right. Yeah.
I forgot to which one was the same day when I took them.
I mean, the first day is quantum and classical, and the second day is.
Yeah.
Or you could just take them all one day,
No.
get it over with.
No.
That's what I did do that.
I wouldn't have wanted to do that because I would have wanted my brain to still be functioning
Yeah.
by the time I got to the last one.
Yeah. Now I take that back. We did 2 days. Yeah. Okay. All right. So we want to see this connection between QFT and condensed matter. And in order to do that, for my sake, we have to review a little thermodynamics. Okay. So here's your definitions that I probably got off of Wikipedia. So a first order transition is a point across which some thermodynamic variable changes discontinuously, right? So like a density of a fluid, magnetization of a ferromagnet, or transition between liquid and gas, or what's the other one? Gas or liquid to solid. Right? And what the terminology is that the thermodynamic quantity, whatever it might be, which changes across this transition is called the order parameter. Okay, it's not going to come up in our discussion, but that's what it's called. So this is, so you can think of these transitions occurring because of temperature, right? So you vary the temperature, and ice turns to liquid, and then it eventually turns into steam, right? But you could, imagine changing some other kind of thermodynamic parameter, like the pressure, right? And you can, you can cause transitions because of this other parameter. And this is what's called a second order phase transition. Okay, so it's transitions because of some other some other kind of thermodynamic quantity. Okay. So, and I think this is what Michael was saying. So you have this critical point, right, where the input of all the first order transitions kind of come together, right? And it's called a critical point, but you also call it a second order phase transition. If you view it from the other way, you can view, the second order phase transition where you go from, one state and it kind of splits into two states. And a concrete example of this is a ferromagnet, and we'll investigate this more. Okay, so here the order parameter is the magnetization. Okay, and we're considering this thing has a preferred axis of magnetization. Okay, so at low temperatures, the spins will line up either parallel or anti-parallel, like we saw in that picture. Okay. Right, and okay, so if we have low temperature, right, and we apply some external magnetic field, we'll get some transition to one of the two possible states, whichever one lowers the energy. Okay, but when we turn the field off, we still have these two states in equilibrium. Okay, right, and so if you change, if you flip on and off or change the direction of the magnetic field, magnetization is going to change discontinuously, right? It's going to flip up, flip down, right? And that's kind of the definition of the second order phase transition. All right. Right. So this is what we were saying that for this ferromagnet, consider when you have fixed low temperature and there's a first order phase transition with no magnetic field. So as you lower the temperature, the spins start to align. Right? But then what if you raise the temperature, right, but you increase the magnetic field? Well, you can get the same type of transitions. Okay. Right. And at some point, there's a critical temperature, which at some point it's like the point of no return. Everything is randomized. Okay. Right. So at this critical temperature, what you have is basically the two thermodynamic states, existing together. Right? So it'd be some weird state where water and ice were existing together. Okay. So this is a picture of, what is this a picture of? So this is a picture of the magnetization, right? As a function of the temperature and the magnetic field, right? So what you would have is, here's the magnetic field, and let's just consider when it's turned off, right? So you would be right here, say at some high temperature, and then you would cool down, right? Cool down, things start to get aligned, you get these, bubbles of alignment. Then you would hit some critical point where everything would lock into position, right? And as you lower the temperature, it's going to, just stay in that thing until you introduce another parameter or another, what's it called? What did I just say? It's just like a some external thing, right? The magnetic field. Okay. All right. So this is what we observe for ferromagnets, and it's also it's the same phenomenon we observe in all those other ones that I mentioned. Okay. And the theory behind this behavior, at least more of a statistical mechanics type of description, was developed by Landau. Okay? And so what I want to do is go through Landau's kind of derivation, his understanding of these types of behaviors, and see where that leads us. Okay. All right. So what he did was he used the Gibbs free energy, which I don't know what the Gibbs free energy is, but I know that I can look it up on Wikipedia, and I know I can find a relationship, or
as someone who's taken both thermodynamics and statistical mechanics, I can proudly tell you that I have no idea either.
There's some other ones too, Gibbs and but isn't there one that's named for somebody?
Helmholtz.
Yeah. All those weird ones, right? But he worked with this Gibbs free energy, okay, which relates, it kind of tells you, it gives you relationships between magnetization and the magnetic field, okay? And he suggested that, if we want to understand this kind of weird behavior at this transition, we should just focus on that region, right? So focus on the region where we're at near zero magnetization, right? And where we're near this critical temperature, okay? Okay, so if we're at very small temperature and we're at very small magnetic fields or magnetizations, we can Taylor expand this thing, right? So we can write down some expansion where the coefficients depend on temperature, and we have some expansion in the magnetization. Okay? And what we note is that there's a symmetry here, right? As I go from M to minus M, if I flip the magnetization, it's independent, right? So it's independent of how I'm looking at it. Okay. So this thing can only have even powers of M, and since M is small, we can always cut this thing off, right? Because it's not like it's just contributions are going to be too small. Okay. So he kept up to the fourth term, and he plugged that into the Gibbs free energy equation, if that's what it's called. And you take a derivative with respect to M, the magnetization, and you get that, right? And we've already said that we're dealing with zero magnetic field, so the other side's zero. Okay? And what you find is that the only solution for that equation is M equals 0, right? It's the only solution, I think. I have to use mathematics to tell me that, but it's 0, right? However, if C, say, for example, if C is greater than 0 and B is negative for some reason, what you have is a non-trivial solution, so a non-zero result, right? Solution for the magnetization below the critical temperature, right? So at above the critical temperature, you're in this region, right? But then say, as you cross over into the, you hit that critical temperature, this parameter B goes negative, right? And if it goes negative, then you go from this nice parabola shape to this more, what we call Mexican hat type of shape, okay? Or wine bottle, the bottom of a wine bottle shape, okay? So this is what the second order phase transition looks like. It goes from the only solution being m equals 0 to some non-zero answer, non-trivial answer. So what he did was say, okay, all right, let me be more concrete, and I'm gonna write these coefficients. So C is going to just be some constant C, independent of the temperature, and B, because I wanted to have this behavior of flipping sign at the critical temperature, I'm going to define it like that. So above TC, it's positive, and below TC, it's negative, right? And then what you find is when you plug that in, you solve for the magnetization, you get some solution that looks like that. So above TC, we saw that the only solution is 0, and below TC, it's that's the solution. Okay. This is the qualitative behavior that we expect at a critical point. So I don't know what that is. There's no figure in slide 11. Yeah, I don't know what I was talking about. I must have been high. Okay. Right. Okay, so that's the case for non-zero magnetic field. Now, what if we put in a magnetic field? Then the Gibbs free energy is going to depend on not only magnetization, but the magnetic field as well, right? So there we would have to somehow incorporate, not only the expansion in temperature and the magnetization, but include some term that includes the magnetic field. So what he did was he took the Gibbs free energy that he'd written down before, and then he just tacked on this term, which minus h times n. Okay, and then what he did, plug it back into the Gibbs free energy equation, take the derivatives, and you get that. Right? Again, you're arguing that. What are you doing? Although the magnetization's on the other side, or the magnetic field's on the other side, so you get some factor of 2 in there. All right. Yeah. And what you find is that the minimum is unique except when h is equal to 0 and t is less than tc. So that goes back to our original case where we had this kind of double dip behavior of the magnetization. All right. So we got a few more slides here before we quit. But what I want to do is, so what Landau did was, okay, let me try to describe this behavior not, through macroscopic or microscopic physics. But let me introduce this idea that the magnetization is somehow related to a field, a spin density field. Right? So a field that describes how the spins are oriented. Okay, and the magnetization is just the volume integral of whatever that density is. Okay? And it obviously depends on position. Okay. Well, if that's the case, then the Gibbs free energy in equation 7, let's see what that is that guy, the guy that we tacked on the magnetic field, becomes this, because I'm replacing m with the volume integral of s. Right? And so what I get is, something that looks like a shearing term. Do you guys remember when we talked about, we were talking first about classical mechanics, and we had the terms, what were the other terms? There was like a rest mass energy term, and there's like a term for moving, and this was kind of a shearing term. So this is like deforming the shape of your field. Okay, that's what I mean by shearing. All right. All right, and it's basically due to this kind of behavior of these. Remember, we have these bubbles of magnetization, or line spins, and they're rubbing up against each other, right? And that's what that shearing term is describing. Okay, so I guess, yeah, the magnetic field obviously is going to depend on, where you are in space, right? Well, what we can do is we can turn on the magnetic field at the origin and see what response we find at another point. And the way we do that is like this, okay? So first, let me take the variation of the Gibbs free energy, right? And I'm assuming that this thing is zero, the variation of the Gibbs free energy. And so then I have to take the variation of the right-hand side, and I do some, here I would do some, here I would do some kind of, integration by parts thing, and I get this delta S that I can pull out, okay? Or delta S. But this delta S is arbitrary, right? It's just like the principle of least action. You use the same type of concept, okay? So you take that to be arbitrary, and it tells you what's inside the square brackets has to vanish. In other words, you get an equation that looks like this, okay? And so now when you're at T greater than the critical temperature, where we've already seen that the magnetization vanishes, there you would expect the spin density to be small. So in other words, what you could do is you could just drop, like, let's say the S cubed term, and you get a linear equation for the spin field, right? Okay, so we've used, same type of mathematics, right? We always use the principle of least action, and we got down to the Klein-Gordon equation, right? That described how that field behaved, right? Here, we're taking the variation of the Gibbs free energy, using some principle from statistical mechanics or thermodynamics, right? And setting it to zero, and then we argue that when we're above the critical temperature, M is small, which means S is small, the field density, right? So we can drop the cube term, we can pull the S field out, and what we get is something that kind of looks like the Klein-Gordon equation, right? It's got a second order derivative times some, some constant p's equals something else, right? And so what we can do is, like I said, we want to, bring in the dependence of the magnetic field on position, right? But what we can do is just imagine a simple case where we turn it on at the origin. We turn the magnetic field on at the origin. It's all centered there, and let's see what happens, okay? So the way we would write that is to just introduce a delta function. Okay, so we're putting all the magnetic field at the origin, okay, and times some constant here in the units. Okay, so that would mean that if I plug that in here, I get this equation. Okay. But what's that equation telling me, Michael? That the spin field is the Green's function of that operator, right? Because it's something operating on the field, and I get a delta function on the right-hand side. That's telling me that it's the Green's function, whatever the hell that means, okay? So it tells us the response at some arbitrary point when the spin at x equals 0 is forced into alignment with H. In other words, so, at that origin, when we turn the magnetic field on, the spins are going to align, okay? But it tells us how the spin density field behaves as a function of distance from that source. Okay? So you can actually solve this equation, right? And you find what the Green's function is. We've done this type of stuff with our Klein-Gordon theory. And actually, this integral that you get should be familiar. It's just in quantum mechanics, when we studied the Yukawa potential, we had a similar integral, and we worked through it. I don't remember if we worked through it or not, but what you can do is you can actually do this equation, and you get something that dies off as an exponential. Okay? We're working in spherical coordinates, so r is just the radial distance. Okay, and this thing that that pops up is something that's called the correlation length. right? Or the range of correlated spin fluctuations. Okay, so it grows and shrinks as you rise or as you raise or lower the temperature. Right? So it gives us an idea of the size of these bubbles, basically. Okay, and you want to notice that as you go towards the critical temperature, this thing goes to 0, which means that this thing's going to blow up, right? Okay, so everything we did, you can see, still depends on these unknown constants, right? B, and then C is hidden somewhere, I don't remember where, okay? But these guys depend on the atomic scale. So for us, like in quantum field theory, those guys would be like the momentum cutoffs. They would depend on the high theory, right? But the power law dependence of this, this solution on this difference in temperatures, it just falls out of the structure of the Landau equations, right? In other words, it's independent of any of the microscopic physics. It's independent of if it's if you're talking about magnetization, or if you're talking about the behavior of these binary alloys, which I gotta look that up on Wikipedia and find out what it is. But any system where you have second order phase transition, this theory is applicable, right? And what it's telling you is that you have near critical points in these second order phase transitions, you have a universal behavior in the dependence of the magnetization and that correlation parameter on other thermodynamic quantities and other quantities on this temperature. Okay. Right. Okay. So, like I said, what it tells us is that at the low or at the small scales, at the low small distance scales, you have the second order phase transition, but it's well defined, it's cutoff independent, and it's nicely behaved. Okay. And I'm going to stop there. Okay. And I'll pick it up next time and talk about the connection between the generating functional and what's the thing called in thermodynamics, the Z partition function. Yeah.
Right.
All right. I don't think that it's not a mistake that we use Z for both. Okay. But I'll talk about that next time. Okay.
This second order condition between it was just condensed matter.
Yeah. But the behavior of condensed matter at small scales is very similar to phase transitions in QFT. Right, so for us, there's a phase transition due to the Higgs potential. Right, so you're at high energies, right? And you have this nice shape, but once you cross that critical energy, it breaks the symmetry and you're left with that double flip. And that's when the Higgs field kicks on.
The beginning of the
Yeah, at high energies, the symmetry is preserved. Yeah. All right. See you next time.